Welcome to BKW Physics. I'm Mr. McConley. And just as a quick recap of what we've been talking about, we've been talking about energy. We left off last time with the amount of work you do will be the same as the amount of potential energy you have, and also the same as the amount of kinetic energy you have if you let an object fall. So we did that work-energy relationship, and we're just going to take it in a little bit different direction today, and we're going to talk about elastic potential energy. So if you have anything spring-loaded, like a little pop gun where you pull the trigger and something gets fired because there's a spring, or if you even have a pen that you click, click, click on that's spring-loaded, there's elastic potential energy there. Another example, they always tell you not to play with rubber bands because rubber bands have elastic potential energy, so when you pull them back, they have this potential energy, and when you let them go, it will turn into a kinetic energy. Okay? Kind of cool. So how does that elastic potential energy play out? In other words, what's the equation? Potential energy is 1/2 kx squared. This is how it is written in your reference table. And the little s indicates of a springy object. I guess that's why they use an S. So this is elastic potential energy. And all energy to this point and continuing from this point will be in joules per units. The K you've never seen before. That's called a spring constant. I'll talk more about that in a minute. And X is the elongation or the compression of the spring. Because remember, and that would be in meters, sorry. Remember, some springs are the type of springs where you stretch them out and they gain the elastic potential energy, like a rubber band. And some springs, like the springs on your car, are different. Springs on your car, they want to remain stretched out, so when you push them down, like you put more weight in your car, they squish down. When the weight comes out of your car, the car would spring back up. Okay, so there's two different types of springs, but either way, this distance here, this x, is how far you move it from its rest position. So if a normal spring has this long of a rest position, and you stretch it out, then the distance you stretched it out, that's the x. Okay? Now let's talk more about this spring constant thing. When you take a spring and you hang masses from it, you hang weights from it, the spring will stretch. And various springs, as you add masses, they'll stretch quicker or less quickly depending on how thick they are. Like if you have a really thick, hefty spring, then the K value will be different than if you had a really light-duty spring like something in your pen. So the K value depends on how heavy-duty the spring is. Now how do you find that? Well, what you usually do is you make yourself a table of the amount of Fg, weight, and the x, the distance that it elongated when you put that weight on. So you put a weight on. Oh, I'll put 10 newtons on. Oh, that stretched it. And you start filling these in. Now, the next step is you actually graph this as force and elongation. You graph force and elongation. When you graph force and elongation, you're going to get a linear relationship, something like this. If you take the slope of this, the slope is the spring constant. So you can kind of imagine in your mind now that you see basically how it works, some graphs are going to be sloped like the red line. Well, that's also a K value, but it's not the same K value as the black line. So depending what the spring is, will depend how steep the slope is. And this part of what we're talking about actually has a name. It's called Hooke's Law. So Hooke's Law is the process by which you find the K value. over here, this equation, elastic potential energy, is simply just an equation that we use to find the potential energy of an elastic object. So for today, physics.